This was like.
I also think, he also did tell me on Monday, and he's like, "You're right."
Page 2 in your packet. We talked about long division. And I want to talk about a shortcut method to that. Okay. So we'll do the same problem on page 2. Now, again, the condition for long division or synthetic division is you're dealing with a fraction, first of all. And you know that power rule is not going to be sufficient because there are more than one term in the denominator. There's only one term in the denominator. We can work with it and just expand. Okay, but anytime you have more than one term in the denominator, that's an indication that we got to do something else. This is not going to be a U substitution problem because U substitution will be a better fit if the degree in the denominator is higher. If the degree in the numerator is either the same or higher, then we have to basically find a way to rewrite this problem so that we can solve it. So again, the purpose of long division or synthetic division is not to solve the problem for you, is to present an easier looking problem for you to solve. Okay, so after we go through long division, we're able to create a problem that is a lot easier to manage because now you're dealing with multiple terms that require only power rule, and then the last term usually is just a U substitution involving natural log. So let's look at a shorter method of long division, but then also I'll talk about pros and cons of both methods. So synthetic division, same problem here. So same issue that we've had before. Multiple terms in the denominator, power rule is not going to be sufficient. But the degree in the numerator is higher, so we have to basically find a way to rewrite this problem first. So synthetic division, you're going to look for a factor in the denominator. So basically, you're going to solve for x. So we're going to set x plus 5 equal to 0. Solve for x. X is -5. So -5 is what you're going to be using. And you're going to put -5 outside a half box. And now you're going to just be pulling the coefficients from each of the terms up in the numerator. Okay. So for x cubed, what's my coefficient? 1. Okay. Now there's a missing degree. What's a missing degree? X squared. Okay, so we need a placeholder for x squared. So placeholder for x squared, what coefficient can we use to represent that? 0. Yeah. So we have a x cubed, x squared. Now we're down to x. So x is -6. And then finally, -20. Okay. Now, first thing we do is we always take the number inside. We go from left to right. The first number inside the half box, you drag it down below the line. Okay, so now you're going to multiply with the outside number. -5 times 1 is -5. You're going to put that on the second row, and then you're going to add. So 0 minus 5 is -5. Put that below the line. Next up, multiply. We get 25. Add 19. Multiply -95. Add again, we get -115. Now, if the last number is 0, that means there's no remainder. But if the last number is anything other than 0, that means this is the remainder. Okay, so let's think about this from a big picture perspective here. I'm taking x cubed and I'm dividing by x. So what's happening is that all my degrees is going to fall by 1. So if I started with x cubed, that means I'm going to end up with what? X squared. And once you have your first starting degree, then you're just going to make every subsequent term fall by 1. So this is x squared. So this must be x. This must be the constant, and this must be the remainder. So this will lead us to a problem that we can now solve. So we get integral of x squared minus 5x plus 19 minus 115 over my divisor. We end up with the same problem that we did using long division, but it's a lot cleaner, a lot less things to keep track of. If we go through this process, power rule, U substitution, we're going to get the same answer. Any questions about this process? So let me talk about pros and cons. The pros of synthetic division is that it's a lot faster, it's a lot cleaner, can get to your answer without having to worry about a lot of these different variables. The downside is that it's a little gimmicky. So like if you don't remember the steps somewhere along the way, then it's kind of hard to figure it out as easily. The second thing is that there's restrictions with synthetic division. It only works if I'm dividing by degree to the first power. If this is degree to the second power, I'm forced to have to go through long division. So synthetic division is nice, quick and easy, but it's gimmicky and it's restricted. So typically, if I see anything degree 1, I just go synthetic division. But if I see anything degree 2 or higher, I have to go through long division. So that's why I wanted to still make sure we understand this process or understand both processes, best case scenario.
Sure. Say degree, are you referring to like the degree of x on the bottom?
Yeah, that's right. So for instance, let's say I had a problem that looked like this. So this presents an issue. If I see this problem, I can't do synthetic. I got to do long division. Yeah. Because of that degree. Okay. All right, any questions there? Okay, let's go to today's topic, which is definite integrals of e to the x. So back to first semester review. Do you guys remember the derivative for e to the u? It's just e to the u times u prime. But basically, the derivative didn't change much. It's basically the same function. We just have to worry about the u prime, which is the case for every derivative. So it should make sense that the antiderivative of e should bring us back to e as well. So since the derivative of e is itself, then the integral of e is basically itself as well. The only complication is that if there is something more than just an x in your exponent, we got to go through u substitution and we have to worry about the leftovers. Okay, but here's the rule. The rule is integral of e to the u du. If I can get my problem to look exactly like this, I can have leftover coefficients, but I can't have any leftover variables. Then I can apply this integral rule, e to the u plus c. Okay, so number 1, says find e to the 3x plus 1 dx. I see that this matches nicely with my e to the u rule. What could be my u value? 3x plus 1, okay. And if you want to use this e to the u rule, you have to let the entire exponent be the u value, okay? If you can't let the entire exponent be the u value, that probably means that there is another rule that we should explore, because this e to the u is very restricted. Okay, if my entire exponent doesn't look exactly like just that u, if it looks like e to the u squared, I don't have a rule to follow. So I have to let my entire exponent represent the u value.
Okay, du dx. What's our derivative? Okay. Solve for dx. Okay, make my substitutions.
What can I? There's no x's to keep track of. There's no x's left. That's nice. What can we push out in front?
1/3. So again, once you get past your coefficient, if your problem doesn't look exactly like the rule, then you can't use it. Okay, so it's got to be a perfect match in order for us to use any rule. Okay, matches perfectly. So now 1/3 e to the u plus c. And then replace the u back in terms of x.
Okay, example 2. Find integral of cosine x e to the sine x dx. We can't just rely on one rule. Because there's a multiplication. We can't think, oh, cosine, I'll do its rule. E, I'll do its rule. That multiplication prevents us from separating. Okay, this is one extended problem here. So too messy for any one rule to handle. We can't separate it. We got to go through u substitution. Okay, so what should be a u value that can make things cleaned up nicely?
Sine x, right? And the nice thing about sine is that its derivative is what? Derivative is positive cosine. Yeah. So that's nice because we know that whatever the derivative is produced,
There is something waiting outside of it to help match and cancel out.
yeah, cosine's derivative is negative sine, right? Okay, so du dx equals cosine x dx equals du. Solve for dx. All right. Nice to see the cosines go away, because if it didn't, then we would not be able to use this rule. Okay, matches nicely here, just e to the u plus c.
Okay, example 3. We always want to think in terms of expanding, but more than one term in the denominator prevents us from expanding. So we're stuck with having to go through u substitution. We can't separate this either. What could be our u value?
So you're probably looking between the numerator and denominator, right? Which one is a u value?
Typically, the denominator being the u value sometimes, or most of the time, is the better fit for things to cancel out. So
We'll let the entire denominator be the u value. Okay. Okay. What's the derivative of e to the x?
yes, right? And so we know that the derivative of e to the x is e to the x, and we see e to the x waiting outside. So that's a good sign that
Whatever derivative we create, we're going to be able to match and pair up with what's available inside the problem. Okay, so du dx, 2 goes to 0, e to the x becomes e to the u times u prime. You don't have to write that 1 there, but I want to keep reminding us that
we're always looking at the exponent to have that u prime if it's anything other than
x. Okay, solve for dx. Make our substitutions. e to the x goes away. Okay. Do we have a rule that fits this? Yes, from yesterday, right? Yesterday, we know 1 over u is not handled by power rule, but you handle using natural log. And replace the u back in terms of x. Let's just do one more and then we can go to review. Okay, so example 4, e to the x cosine e to the x dx. We can't separate this and say, okay, I'll handle e to the x and then I'll handle cosine e to the x, right? These are connected. So we got to go through u substitution because there's no one rule that can handle all this going on. So if you had to guess, what could be your u value? There's 2 of them. Do we do both of them? Do you do one of them? Which one could be a better u value here? What's inside of parentheses? Yeah, if you're a lot of a rule of thumb is if you see a set of parentheses, that could be a u value, right? Why do we not want to let both be the u value? Yeah, we want to save one, right? We're saving one in preparation for the derivative that's going to come out of it, and we want things to pair up nicely. Yeah. What's the what?
What's the
Yeah, good question. If it was like integral of e to the x cosecant of e to the x cotangent of e to the x, then I will let both of these be the u value because I'm trying to get it to look like this. So in a scenario where I'm trying to make it turn into a specific rule that's usable, then I would select multiple u values because I have a formula in mind that I'm trying to work towards. Yeah. But this one, I'm trying to work towards the cosine of u. So okay, du dx is e to the u times u prime. We make our substitutions. So just like what we suspected, we are able to save the e to the x and cancel out. And now we have a perfect match with a rule that's available to us. Okay. What's the antiderivative of cosine? Positive sign, yeah. And then finally replace the u back in terms of x. Okay, review packets. Let's go to page 7. Okay, so let's go back to Riemann sums. So an important key point that I want you to keep in mind, that I want you to have in mind is when you're applying a calculus process, whether a derivative or integral, your units of measure must change, right? So if you find the derivative,
you know that you're gonna keep adding more rates, right? So if you start out with ounces, then you end up with ounces per minute, then ounces per minute squared. But if you take the antiderivative, then ounces per minute will become what? Just ounces, right? So you're stripping away that denominator each time you take the antiderivative. Okay. Also, think in terms of area, right? If you think in terms of area, if I have ounces per minute multiplied by minutes, that's why it's strips away, right? So that multiplication process is going to take away one of your units. But if you're dividing, which is derivative slope, right, meters becomes meters per second, and you're adding more and more rates to it. Okay, so here, this is hot water is dripping through a coffee maker, filling a large cup with coffee. The rate that water in the cup is changing is given by a differential function C of t. So that differential function, that just means smooth curve. There's no sudden jumps. So that means at 0 minutes, there's no water entering in. 1 minute in, the rate is 5.1 ounces per minute. And then it starts slowing down after the 3rd, 6th, 9th, and 10th minute. Right. So it says interpret the meaning of C prime of 6. C prime of 6. Okay, so C prime of 6 is off this table. So C prime of 6 is 3.3. I'm sorry. C of 6 is ounces per minute. So C prime of 6 is going to be, it's going to be the rate of change of this. Okay. So what we can say is C prime of 6 tells us the rate is changing. So I want to point something out here. C of 6 is already a rate. Right, C of 6 is already a rate because we know C is already ounces per minute. So C is just the rate of water added. Right? But then C prime is a rate on top of a rate. So you use the word how fast to indicate that there's a rate going on. Does that make sense? So I think again, what a lot of students want to use when they know that there's a second derivative going on, they want to say velocity or acceleration. Okay? But we don't want to use those words unless it's a particle motion problem. Okay? So you want to say the rate is changing or how fast the rate is changing to indicate a rate of a rate. Okay? So it says approximate the value of C prime of 6. So if we're talking about a rate, if we have a table of values, what can we do? What operation can we do to find a rate of this at this point? Find the what? Right. Normally we would find the derivative, but we don't have a function to find the derivative, but we can find the slope. So to find the slope, we just pick what? Pick 2 order pairs close to your target, right? So either use these 2, you can use these 2, you can even use these 2, but you just want to stay as close to your source as possible. So I'm going to choose these 2 here, but you could,
you know, you may get different answers, but as long as your process is right, that's. So change in ounces per minute divided by the change in time. So we can say that at 6 minutes, the rate at which water is being added to the cup is decreasing by 0.7 ounces per minute squared. Okay, interpret the meaning of the integral from 1 to 10 of C of t dt, indicating the units of measure. So this is ounces per minute. So we know that the antiderivative will be in terms of what? Ounces, right? Ounces. But let's think about first theorem here. The integral from 1 to 10 of C of t. Imagine C of t becoming its antiderivative, becoming uppercase C of 10 minus uppercase C of 1. So what does that mean? This is telling us the change in the amount of coffee in the cup, right? So C of 10 would be how much coffee, how many ounces of coffee are in the cup at 10 minutes. This is telling us how much coffee is in the cup at 1 minute. And between 1 to 10 is what's the change in the amount of coffee in the cup or in the in the cup between 1 and 10 minutes. In other words, this is basically looking to see how much coffee has been added to the cup between the first and 10th minute. That's what that integral from 1 to 10 of C of t tells you. It accumulates all those rates over that period of time, and what you end up with is the amount of coffee added into the cup. A part D says, now let's approximate the integral from 1 to 10 of C of t using two middle rectangles. So now we're going to use what we've done with area formula, right? Two middle rectangles from 1 to 10. So I'll do 1 to 6 and for 6 to 10. What's the width of my two rectangles? 6 minus 1 is 5, and then 10 minus 6 is 4. And then the height I'm going to choose is 4.2 and 1.2. Yeah. To 21 plus 4.8. Again, why do we not leave this as ounces per minute? Integral, good, right? If we're starting with ounces per minute, we're gonna have to change the bounds, strip away that rates, and we got to change the units to ounces. Okay, last part here approximates the average rate of water being added on this time interval from 1 to 10 using the results from D. So average rate, this is average value theorem. We're trying to find average value of C of t, which is the average rate. So average value theorem, 1 over b minus a. So 1 over my a and b values are 1 and 10. So 1 over 9
integral from 1 to 10 of c of t dt. We already got that approximation from part D, so we can just bring that part in. And then our average rate is 2.867. That should make sense. It should be something that falls in the range of what we see here, right? If you're just looking at these numbers and just trying to do an approximation between 0 and 5.1, you would say somewhere in that 2 to 3 range, right? And it should be consistent with what you would expect. Okay, let's do page 8. Very much the same process, but now we're going back to units to particle motion. All right, so Joanna jogs along a straight path between 0 and 40 minutes. Her velocity is given by a differential function. Selected values of v of t, where t is measured in minutes and v of t is measured in meters per minute, are given in the table above. So let's just kind of imagine what's going on with her jog. So 0, she hasn't started yet. 12 minutes in, she's going at 200 meters per minute. 20 minutes in, she's picking up her speed, 240 meters per minute. What's happening at 24? She's what? Another word for, what does that mean? Down. Yeah, so she's running along a straight path, right? She obviously has to turn around and she's backtracking, right? So she's running towards where she started. So that negative 220 means that she's backtracking, right, along that straight path. But then by the 40th minute, she must have turned around somewhere along that time frame, and she's back running in the forward direction. Okay, so interpret the meaning of v prime of 20 and indicate units of measure. So anytime I see prime, I know you want to say acceleration, which is fine, but another way to say it is what? Rate of change of velocity. Yeah. So I think if you can get into the habit of saying that, instead of always using acceleration, in this case, it works, acceleration, but AP exam, College Board, they want to see students understand and use that rate of change whenever they see a derivative notation. Okay, and then what units should this be in? Minus squared, yeah. Every time you find a derivative, your denominator, you're adding more and more rates to your denominator. Every time you take the antiderivative, you're stripping away the rates from your denominator. Okay, approximate v prime of 18. So I can just find the what? Slope. And here, we should only be looking at one way of doing this. What would you do here? Yeah, 12 and 20, right? There's only 2 order pairs that you can choose. In this case, any other order pairs is going to feel too far away. Right? You want to get as close to your source as possible. Approximately. So change in velocity over change in time. Okay, interpret the meaning of the depth integral from 20 to 40 of v of t. Well, why don't we use first theorem and put it in a form maybe that's easier for us to say it in words. So what's going to happen with velocity? Velocity turns into what? Position, right? So I'll use x. So x of 40 minus x of 20. So what's a way that we can say this similar to how we said we interpreted on the previous page? Change in position, or you even say change in distance. Change in position or change in distance between 20 and 40 minutes. So basically, what this is going to give us is going to give us between 20 and 40 minutes, what's going to be the distance between those 2 points. And what units of measure do we expect out of this? V of t is going to turn into just meters, right? Change in distance or change in displacement or change in position, those are all fine between 20 and 40 minutes. Units is meters. Okay, approximate the value using 2 trapezoids. So 1/2 width, height 1 plus height 2. 2 trapezoids from 20 to 40. So we get a negative number, which is okay, because that just means negative 520 meters means that between 20 and 40 minutes, she's going to end up 520 meters to the left of where she began. So she's basically, for a large part of it, she's running backwards, or she's running towards her starting line. A last part, approximate her average velocity, so average value theorem. So 1 over b minus a, and it says use the results from part D. We already have that approximation for 20 to 40. So we just take that divided by 20. So basically, what is her average velocity? She's in that time interval, she's running at 26 meters per minute in the opposite direction. Okay, any questions here? So during the help session today, I went over pages 4, 3, and 4. So I just want to kind of run through, make sure that we
understand the process involved with these derivative graphs. So let me just kind of run through. Okay, page 4. I'm not gonna do the whole problem. I just want to kind of talk about the process here. So page 4, we talked about how if you're given this relationship here, you understand that we have 3 levels of information that we got to build, right? We know H is the area under the F graph. We know H prime is the F graph itself. So we know H double prime is the F prime graph, or F prime of X. So for A, B, and C, it's just asking for you to find the area, right? So you follow the direction here. If you need to flip the balance, you flip it. Otherwise, you're just grabbing the area from what's between the x-axis and the graph. And then when you get to part E, it says H prime of 3. H prime of 3 is F of 3. That's the order pair. So that's just Y value of 2. And the H double prime of 9.5 is F prime of 9.5, which is the slope. And the slope of F here is a 1, because I'm just going to just do rise over 1 to get the slope of that line. Okay. Understand that this is the derivative graph of H. So if you mark up your graph accordingly, you can create your derivative sign line. Above is positive slope, below is negative slope. Anything on the x-axis is slope 0. And then once you create your derivative sign line, then you can look at your arrows and decide where is there a relative max, where is there a relative min, where is the increasing and decreasing occurring. And finally, you need to be able to apply extreme value theorem. So looking at your slope sign line, you know that all these are candidates because I got to include endpoints and I got to test relative min and relative max. So I need to find H of 0, H of 1, H of 6, H of 10, H of 11. So all of them can be pulled from your H of X definition. But the nice thing about this problem is that a lot of the order pairs that you need is already found from A through D. So then I just found the missing one that that was not asked of me before. And I just used the definition to find that Y value. And then finally, we have all of these options in front of me. These are all the candidates. I'm just picking off the highest and lowest Y value. Highest Y value is 0. Lowest Y value is -6. So those are my absolute max and absolute min. So tomorrow morning, I'm going to go over the morning review, and the morning review has one of each type. So particle motion, using a lot of calculator, using graphing features on page 11. And then derivative graph. EVT is involved, derivative graph is involved. Okay. And then table of values, interpreting units of measure, interpreting what a derivative and integral means for this process. All right, so I'm going to go over that tomorrow morning, but I encourage you guys to work through it ahead of time. So tomorrow morning, if you come, if you have specific questions, you can ask them. The key is also attached, so you can definitely check your answers. And I also have a video from last year that you can watch of me going through this. Okay. All right, you guys can come up and get your phones. If you have any questions about your calculator, come and ask me, and I can help you with any keystrokes that you need to see.
That's is it gonna be one of these and then one of the graph?
Oh, that's correct. That would be 3. Yeah. Yeah.
And then,
Yeah. Tomorrow's problem just three problems. Okay, 3 problems, 3 pages.
so my graphing calculator yesterday didn't work.
Mhm.
If I just rewatch the video from yesterday, will I be able to see everything you know how to do on the graphing calculator?
I think so. Or if you wanna come in sometime, I can show you all you can practice the keystrokes on my calculator. Yeah, good period.
Yeah.
Yeah, I can help you.
Sure.
On this one, it's more like graph and find the values, but I did function.
So it's a little bit harder on this one. I can show you. No, it's just from what we've done. Yeah. Yeah, we could take one of the old, I think one of the older, graphs. So this is what the graph looks like, right? Obviously, you can't get to the graph. But what you can do is, you go to table, edit function, and let's say you want to look for that point, right? So you get edit function. And then let's say you want to start at 0. So let's just start at 0, and then right now it's set by 1, okay, so it's kind of system. Now, what you're looking for is you're looking to see where does the lines out came from. Looking for what else, there it is. You know, between 2 and 3 is going to change that. So that's not very accurate. What we're going to do is go back to table, edit function. Now you're going to start at 1, you go to 1 and 2, but then you're going to make your steps go smaller. Let's take good point. You're going to step through your order pair.
Do you have to start at one? Or does it matter?
Oh, sorry, yeah, I guess you can start at 2 because you know it's in there, so table edit function.
Like if you start from 0 to 0.
It doesn't matter, but because you know there's nothing here, I can start it. Yeah, it's faster because you're smaller, your steps going to take longer to go through. So I'm going to start at 2 because I know it's between 2 and 3, which will same with time. So I do 0.1 here. And then it's, you know, the interval slower, but here I know it's being 2.5 and 2.6. Oh, it's saying 2.4 and 2.5. That's what it's not. Go back again. Make it even more, even smaller, 0.01. Start at 2.4. There we go.
So how much accuracy do you need for the test?
For the test, because you're using the Pro, you should be full places. In this case, you're going to pull the area from the side. So the interval from 0 to 6 is just that area.
Okay, so there.
So it's just triangle, rectangle.
Okay.
Above the positive, below is negative.
Gotcha.
If you pull the negative out, that's good. So it'll be 6. And it'll be negative.
Okay.
You only would do this if there's an actual function where you find it. Here you don't have the function to find it, so you gotta rely on the area.
Okay, you can't just plug it in with it.
Yeah, well, yeah, because this is not the anti-gravity trap, this is the really dust. So we're not able to get an accurate reading.
Okay.
Oh, right, that's right. Morning or lunch?
What's yours? I understood what.
Oh,
I can, or I can, whichever.
it's up to you. It's, I mean, my hair period is, just face it back, so fourth period is fine, and fifth period, that's it.
Okay. Oh, I'm going to annoy you.
Guys, these are the photocopies of the homework pages. So homework's not due until Monday, but I don't know if you guys got a chance to pick one of these up, so make sure. I didn't get a chance to give this to you yesterday, so.
It's have people to hang out with, that's why I hope it's really.
Yeah, so let's start negative 10 to 10. And then if the problem says 0 to 5.
What was the last four?
0 to 5.
Hours.
And if you look at your graph, you realize, wait,
Okay.
I'm not
It's-
seeing
it's
some parts,
honestly
then you go back and change your life.
I'm just like dreading it because it's like, I would just rather.
Yeah.
Yeah.
Thing is, I think we test though, like, lots of things. I like to say that. I should, with the person. It's alright. It's not a good. It's
See, like, he says that, but like, I don't think I would actually ever
It's
say
not
that.
that. I'll put it with.
I don't think he could like, I don't, like, I can't think of a punishment. He probably just.
A punishment for, yeah.